October 2020, a Scottish Championship match, Inverness Caledonian Thistle versus Ayr United. A newly installed automated camera designed to broadcast the game by tracking the ball instead spent the afternoon zooming in on the bald head of a linesman standing on the sideline. It was not a bug, it was the architecture working as designed. The system saw a round, illuminated, light-colored object under stadium floodlights. In the lexicon of computer vision, the linesman's head was a ball. The pixels were right, the physics was wrong. This is the limit of every enterprise vision system built on pure pattern matching. Object detection is not object understanding. The next frontier is not larger parameter counts. It is physics-constrained vision. Generic computer vision fails for three reasons that have nothing to do with the camera. First, texture bias. Convolutional neural networks rank candidates by the highest confidence score. Under Stadium Glint, the head reads at 98%. The actual ball, blurring through shadow, reads at 80%. The system locks onto the head. Second, frame-independent inference. The detector analyzes one frame, forgets, and analyzes the next. There is no constraint that the object cannot teleport 15 meters between frames. Third, no object permanence. When a player blocks the ball for a fraction of a second, the tracker declares it lost. The same failure mode shows up in retail when a hand obscures a SKU on the highway and on a wafer line. The Veriprajna remedy treats the neural network not as a fact, but as a noisy measurement that must be validated against the immutable laws of physics. The pipeline runs in 4 stages. Stage 1. A standard convolutional detector YOLO efficient det produces candidate bounding boxes. These are hypotheses, not answers. Stage 2. A Kalman filter maintains a probabilistic belief about the object's position, velocity, and acceleration. Before the next frame arrives, it predicts where the ball must be from Newtonian mechanics. The vision system returns 2 candidates, one near the prediction, one 15 meters away on the linesman's head. The filter computes the Mahalanobis distance, the number of standard deviations between prediction and measurement. If that distance exceeds 3 sigma, the candidate is rejected as a kinematic outlier, regardless of its visual confidence score. Stage 3. Optical flow becomes a hard constraint. A soccer ball in flight generates a specific pixel velocity field. A stationary linesman generates a near-zero field. If the detector says ball, but the optical flow at that region indicates the object is stationary relative to the ground, the detection is invalidated immediately. Stage 4. For complex dynamics, the Magnus effect curve on a free-kick fluid flow in an industrial pipe. Robotic arm manipulation, a physics-informed neural network adds a regularization term to the loss function. Loss total equals loss data plus lambda times loss physics. The network is penalized not just for missing the target, but for violating the governing differential equation. It learns gravity. It learns momentum. It learns the rules of the game, not just the history of the game. The same physics layer transfers across industries. In sports, 3-dimensional Kalman filters reconstruct the ball's depth from scale changes and from the constraint that vertical acceleration must equal -g. The camera pans ahead of the action instead of reacting to it. In semiconductor manufacturing, multi-view geometry catches the false defect that wrecks yield. A real pit on the wafer shifts position predictably under parallax. A surface stain does not. If a defect candidate fails the triangulation constraint, it is dismissed as a surface artifact, and the wafer is saved from scrap. Industry research indicates that improving defect detection accuracy by just 1% yields a 5 to 10% increase in first-pass yield, millions of dollars per fab per year. In autonomous vehicles, phantom braking is a vision system that mistook a shadow for a wall. Optical flow over several frames reveals zero height relative to the road plane. A radar return confirms empty space. Physics arbitrates, the brake is not pressed. This reframes the build versus buy decision for any engineering leader. Generic APs reach 90% accuracy quickly and cheaply. 90% is enough for a demo. 90% is not enough for production. The business value and the business risk lies entirely in the last 10%, the bald head, the shadow on the road, the rare defect, the occluded item in a basket. Wrapper A's scale costs, scale errors, and surrender intellectual property. A physics-constrained system carries a higher initial engineering cost, but it owns the model, the logic, and the moat. For a mission-critical task, the calculus is not subtle. This is what we mean by deep AI. The white paper walks through Kalman filters, optical flow, physics-informed networks, and Hamiltonian neural networks applied across sports, semiconductors, and autonomous systems. Veriprajna, deep AI solutions for a deterministic world.